So we've talked about scatter plots and correlation and how we take a scatter plot and we fit a line on it called the line of best fit or the least squares regression line. And we talked a little bit about how we place that line on it. So we place that line in such a way that the square of the residuals, the sum of the squares of the residuals, are as small as possible. Really what we're going to look at here is we're going to look at residuals a little more, and then we're going to look at a couple of really this has to do with variation in the line between the points and the actual line. So we're really going to look at how well does the line fit? How good is it? Okay, that's really what we're going to be answering in this. If you remember from last class, residuals represents the vertical distance between a linear model's actual data value and the data value that is predicted by the least squares regression line equation. So remember, you make sure you do it in the right order. So the residual is the actual minus the predicted. The actual is y, the predicted is y hat. So we subtract those two. If it's positive, that means that the actual value is greater than that predicted by the least squares regression line. If it's negative, that means the actual value is lower than that predicted by the least squares regression line. So we looked at this example in the last lesson between percent school days attended and the raw score on a particular type of test, a state test. Okay. And we got the equation y hat equals negative 7.69 plus 0.57. Where where y hat is the predicted test score, x is the percent of school days attended. What does negative 7.69 represent in this equation? No, we haven't found that yet. No, has nothing to do with that. What's in a least squares regression line equation? There's x, there's y hat. What are the other two things that are in there? Y-intercept and slope. So which one's this? It's the y-intercept. The slope is the coefficient of x. Okay? So negative 7.69 tells us what would the score be if there was 0% attendance. And that doesn't make any sense, okay, because you can't have a negative test score. So remember I talked about how to explain the meaning of the y-intercept and whether it actually has meaning in a specific example. The slope means that for every 1% increase in attendance, the test score mark will go up by 0.57. Okay, remember slope is rise over run. That doesn't change. Okay, so new student comes to the school. And, oh, by the way, I'm going to ask you this, since we had a little talk about it during pre-cal. How confident are you in the predictions? That was a question in the lesson practice, a different example. How do you think you would answer that question? Just by looking at this. Why would you say you're fairly confident? Yeah. Confidence talks about like how close are all the points to the line. Okay? They're all pretty close. We're confident. If, however, this one was up here, and this one was down here, and this one was down here, and this one was up here, we'd be less confident. Okay? The difference between the line and all the points is pretty small. Anyway, new student comes to the school, his attendance rate is 80%. How would you find his predicted test score?
May not go up over that.
I suppose you could.
We could.
Could we be a little bit more accurate?
That's bad, yeah.
Okay. Could we actually not find the score? By saying, okay, I'm going, this is X, 80%. I'm going to plug it in here. Therefore, the predicted test score is going to be whatever I get when I calculate that, which is 37.91. That's what the line's predicting. And you're right, if you actually went here, if you went up at 80 and then went across, notice we're going to be at 37.91. Okay? But this student writes it and gets a 44, so gets 44 points. So this represents the action. Okay? This is the actual. You can't find the residual unless you have the two values, actual and predicted. And a lot of times you're going to have to calculate the predicted using the regression equation. So this is predicted. Once we've got that, find the residual. It's actual 44 minus predicted 37.91 gives us what, 6.09? Positive 6.09 points. So it's a, make sure I did that right, yeah. So it's positive residual. So we did this part, but we still got to do this part. How would you interpret it? Is actual test score is higher than predicted by 6.91 points. That's the interpretation. Okay. Okay. You can actually graph, like here, I could find residuals for all 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, 11. I could find the residuals for all 11. This one would be a little bit positive, this one would be more positive, this one would be, looks like slightly negative, little negative, little negative, little negative, a little bit more negative, etc. Okay? And I can plot those differences. And what we call that is a residual plot. So here is a new example where we've got all these values. So what this represents is I'm taking the first X value here, it's positive residual, isn't it? Because it's above the line. So this same value, it's above 0. It's above the line. This one goes here. This one goes here. So that one goes there. That one goes there. That one goes there. So I'm taking from a scatter plot, I'm making a residual plot. The reason why I'm doing that is because I want to see, can I actually use a line in this question? Okay. So if you look at this, Yeah, these dots, they pretty much form a line, don't they? And notice when I plot all the residual differences, all the points are pretty scattered around, aren't they? If I look at this next example, is this a line or more of a curve? That's more of a curve, isn't it? We tried to fit a line in it, okay? And when we plotted the residuals, notice we got a curved pattern. If that happens, a least squares regression line is not good to use. Because if the original data isn't linear, remember least squares regression lines are linear, right? So if the original data is following some sort of curve, we don't want to use it. It's not a good predictor at all, so we don't even want to use it. So we can look at the residual plot and it tells us whether we can use it or not. If it's all scattered about, looks like it's randomly scattered, a line is good. If it's a leftover curve pattern, like if it goes like this, or if it goes like this, a least squares regression line is not good to use. Okay. So does this linear model provide a good fit? Yes. No leftover curve pattern. In the residual plot. It's randomly scattered. Okay. But the next one, no. Not a good fit. Because there is a leftover curve pattern. In the residual plot. Okay. So this tells us, you know, should we use a line? Yes. Here, no here. The next thing we want to look at is, like I said, first of all, should we use a line or not? And second of all, how good is that? Now this looks a little messy and complicated, but here's what it comes down to. So during COVID, a lot of universities and colleges in the States, they dropped the SAT, ACT requirements. Okay. Once COVID ended and people started going back to colleges, some still have them as optional, but slowly most colleges and universities are bringing them back again. Okay, SATs or ACTs. So in 2020, the university system in the University of California, okay, which has tons of universities in it, University of California, San Diego, University of California, Berkeley, University of California, Los Angeles. It's a whole bunch of universities, okay? They're all called University of California, and then wherever they're specifically located, they're given that additional name. Anyway, they released a study showing how good do standardized test scores like the ACT and SAT predict their college marks or GPA compared to how good does their high school average predict how well they're going to do in college. Okay, because I mean, this is what they base a lot of their admissions on. Okay, not everything. There's other things that you have to present as well. Okay, but I mean, like in general, if you've got a strong high school GPA and you write a strong college entrance exam, you're probably going to do well. Okay, it's probably a good sign. If you know, you maybe didn't have the highest high school marks, but you had a high entrance exam that you wrote, again, that could be a good predictor. Okay. The question is, which one is the best predictor? So they tried 3 different things. And here's the scatter plots. First thing, the relationship between how a student did in high school on a scale from 1 to 4, okay, versus how they did in college on a scale of 1 to 4. Second one was how they did on the SAT, okay, and what their college GPA was. And the third one was, what if we made a combined mark out of how they did in high school and how they did in on the standardized test? Is that a good predictor? So we're trying to figure out what's the best predictor. So just so you have an idea of how to use this graph, okay? Use the first one to predict the first year college GPA of a student who has a 3.5 GPA in high school. Well, obviously, the most accurate answer would be if we had an equation, right? But we don't. So that's when we go to the graph. So 3.5 looks like about what? You can probably be more accurate than I can, but 3? Does it hit around 3 or a little higher than 3? I don't know, you tell me. I get, from what mine is, I get approximately 3.0 GPA or college GPA. What line to you, or which of the following 3 graphs looks like it's the best fit? Of which the 3 would you say would be the best fit?
Okay.
Second? Everybody agree? Anybody else have a different one? Okay, how about this? How about the first compared to these 2? Not really, eh? Like, there's something interesting happening here. Notice with the high school GPA, boy, there doesn't seem to be a lot of low GPAs in high school. Like, it's going up, you know, the higher your high school GPA, the higher your college GPA is predicted to be. But like, look at here, not a lot. And yet with the SAT, there is a lot. And when we combine the 2, there's still a fair amount. That's an interesting question. What do you think is happening in high school that's causing this? Nothing? Why is it that there's so few or so much fewer lower GPAs, high school GPAs, than higher ones? What's happening in schools? Zara?
Schools are grading.
There you go, grade inflation. Okay, which is something that's, I mean, that's why a lot of universities went to having to do a written part of an application, even in Canada. Because what happened is that your averages were getting so high, they couldn't differentiate between students. So they had to add something else. So that's why a lot of schools like UBC, like McMaster, okay, like Western. One school didn't, they still base it just on grades, and that's McGill. Okay, Queens, you have to write something up because they want to try and differentiate because of grade inflation. So yeah, this is, I mean, it's a little tough to tell between these two, which one looks like it would be the better one. Okay? I would go so far to say as maybe this might be better than this one, but not by much. Okay? This one looks like it fits a little better, where this one looks like it's, they're still pretty spread out. So if I was to take a guess, I would probably say the third scatter plot, but not by much. But not, and that's compared to the second. First one's definitely up. But it's pretty close between the second and third. Okay? But we need to do better than that. So we need some measurements. We need to figure out how spread out is or are the dots from the least squares regression line. Thank God, I thought I was the only one that was getting hot. Is it hot in here? No? Feels hot to do. Anyway, there's a couple of measurements we can use. One, you're familiar with, standard deviation. Okay? Standard deviation, what you've learned is that in a data distribution, what's the typical distance between a data value and the mean? That's what standard deviation means in a one variable set. But in this, we talk about the standard deviation of the variables. In other words, of the residuals. In other words, what's the typical distance the residuals are from the line? Or what's the average error or typical error? I could say error or distance. We're not going to calculate these. You're going to be given them, and then you interpret them as to whether it's good, it's not so good. So here, if you look at a couple of examples, this one, all these orange lines, those are the residuals. All five of those are pretty close to the line. So therefore, there's a stronger correlation, so S will be lower. Okay? The smaller S is, the better. That means that the points are closer to the line overall. Weaker correlation, S is higher. Okay? Did I say that right? Stronger correlation, S is low. Yeah, that's right. Here's how we interpret it. This is kind of the sentence that you use when you are asked to interpret the standard deviation of the residuals. You would say, when using the least squares regression line with whatever the explanatory variable is to predict whatever the response variable is, will typically be off by about how many units of the response variable. So in this one, we are told that S is 1.99. And this is back to our percent school days attended and test score. So how would we interpret it? Well, we'd use this, but instead of explanatory and response, we write percent attended and test score. So when using the least squares regression with percent attended to predict test score, we will typically be off by 1.19, and then the units of the response variable, which is points. Okay. So when using the least squares regression line with percent attended to predict test score, will typically be off by about 1.99. So going back to the three graphs, S was calculated. Here, we were off by about typically off by about 0.563 college GPA points. Here, off a little less. Here, this was the best one. Okay, so because remember, the lower S is, the less variable it is. So that means they're all tighter to the line. In general, they're all tighter to the line. Okay. So what's the best predictor? According to the standard deviation of the residuals, combined high school GPA and SAT score. That gives us the lowest variation. Okay. The other way we can measure how good a line is and what the best line is from choice is something called the coefficient of determination, or in other words, R squared. And yes, that's related to R. Okay. So we did this when we first started this unit, when we talked about correlation and the correlation coefficient. The coefficient of determination is when we take the correlation coefficient and square it. So if I square all these, well, 1 squared is 1, 0.9 squared is approximately 0.83. This is approximately 0.23. Obviously, this is 0. Negative 0.48 squared is the same as 0.48 squared. Negative 0.91 squared is the same as 0.91 squared. Negative 1 squared is 1. Notice they're always positive values because we square them. Okay. The closer, like correlation, the closer R squared is to 0, the weaker the correlation or the relationship is. If it's close to 1, it's strong. If it is 1, it's perfect, which means that every point is on the least squares regression line, like so. Okay. So in this case, the line that we use perfectly explains the data. Here, well, all the points aren't on the line, but reasonably close. So we would say the linear model explains, and we always want to write it as percent, 72% of the data's pattern. What does that mean? That means that 72% can be accounted for between, or can be accounted by the relationship between the two that we're measuring. 28%, something else is at play. Something else is causing it. Okay, that's really all you need to know. Here's how we would write the interpretation for R squared. Okay, so you would say R squared as a percent of the variation in whatever the response variable is can be explained by the linear relationship with whatever the explanatory variable is. So let's say, going back to our three graphs, we are asked, and notice again, this one's the best because it's closer to 0 compared to the rest of them. It's not great. There's a lot of variation here because this percent is pretty low. Obviously, the higher percent, the better it is. Okay, so we want to interpret this one though. Okay, high school GPA and college GPA. So we would say 13% of the variation in college GPA can be explained or predicted, can be explained by the linear relationship with high school GPA. That's not a big percentage. That's not great. Okay, that means there's a lot of other factors at play here. What other factors could explain a higher GPA? What are the things? Anything? How about how wealthy your family is?
Some people are bad at taking tests. They could have like done good at school and then fall obviously.
Yes? Okay, well, this is just high school GPA.
Or
Right. So, but yeah, I mean, that could be one reason. There could be a whole bunch of factors. We just don't know what they are. All we know is that quite a bit can be explained by something else besides high school GPA, which makes sense because we just saw from this whole thing that high school GPA wasn't the greatest predictor by itself of college GPA. Okay. One thing we're going to do to wrap up. Oh, sorry. Forgot to answer this question. Does including SAT scores substantially improve the strength of predictions? Well, if it was just, what was R squared when it was just high school? 13%. What was it when we combined high school and SAT? 26%. Not great, but double what we had. So better, right? So substantially improved? I don't know about substantial. It improves it. In fact, it doubles the percent. but 26% is still fairly low. I mean, we want to be up in the 70s or higher. That means that line fits really well if we're up in the 70% or higher. If it's down here, you know, it's low, it's fairly low. There could be a lot of other factors at play. Finally, outliers. What do outliers do to all these measurements that we talked about? Y-intercept, slope, S and R squared. First of all, we need to establish what's an outlier. One of these three is not an outlier. Can you guess which one? C is not an outlier? A? Who said A? Why? Because if you extended the line, this point would be pretty much right on. Okay? Outliers are far away from the line vertically. So B and C, I mean, C, maybe not so much. It's iffy. B, definitely an outlier. Okay? So A, no, because if we extended the line, the point would be right on it. B, yes, because compared to the three other points, that's quite a distance away. C, the technical math term would be iffy. Don't look at me like that. Don't judge me. Because it's your birthday, you think you can do whatever you want. You walk around like you own the place. Okay. So what does an outlier do? Well, it's going to have a big impact on the correlation, on the coefficient of determination, and the standard deviation of the residuals. So as an example, no outlier, we've got a pretty strong relationship. Okay? We've got, you know, even R squared, fairly high. 62% can be predicted by the least squares regression line. But if we put that outlier in, all of a sudden, we're down to negative 0.61. Which means that R squared goes down to 0.37, drops significantly. And S, even though it may not look like a lot, it did increase quite significantly. So outliers will change R squared and S, depending how far they are from the least squares regression line. Obviously, the further they are, the bigger the change is going to be to those three variables. Okay. Again, we're not worried about how to calculate these. We're more worried about how to interpret them. Okay. Okay. So for next Monday,